Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 12, Lesson 4 on non-uniform probabilities. So far, all of the probabilities we've looked at when we're rolling a die or spinning a pointer or what have you, every outcome that we've considered has been equally likely to every other outcome. All right, and we can then use that to come up with the probability of a variety of different things happening. Today what we're going to do is we're going to look at a few cases of non-uniform probability. Now, in order to do this lesson, you're going to need to have two coins that you can kind of flip, or I guess you could have one coin and flip it twice, and you're going to need to have two standard six-sided dice, okay? So make sure to have both of those before we get going. And let's do it. All right, so let's take a look at exercise number 1. For this exercise, you will need two coins. Let's try an experiment where we toss the two coins and record what they both land on. Letter A, there are three possible things, which we call events in probability, that can happen when tossing two coins. What are they? All right, so pause the video now and imagine tossing two coins and looking at what you see. I claim that there are three distinct things that could show up. What are they? Pause the video now and write them down. All right, well, it's pretty simple, right? You could get two heads. You could get two tails. Whoops. Let me try to spell that right and maybe make it look right. Two tails or one head and one tail. Right? That's it, right? That is all that can happen. Don't get snarky on me and be like, well, they could land on their sides. No, sorry. You could get two heads, you could get two tails, and you could get one head and one tail. That's it. Now, what I'd like you to do is play around with this a little bit. So I want you to take those two coins, and you could do this with a partner or you could do it by yourself, and I want you to flip, all right? And what you're going to want to do is you're going to want to label this dot plot. In fact, why don't we label it all the same? So like you got two heads, a head and a head, a head and a tail and a tail, okay? So what I want you to do, maybe label this diagram the same way, flip those two coins. If you get like a tail and a head, put a dot here. If you get a tail and a tail, put a dot there, a head and a head, put a dot there. And I want you to do that 20 times and then kind of rack up the dots. You should eventually obviously have 20 dots, not 40. Okay, each time you flip two coins, that's a single thing, a single dot. I want you to run that experiment and just draw up your dot plot, see what you get. Pause the video now and take some time. This could take up to maybe like 5 or 10 minutes to do this experiment. Now, no way for me to know what results you got, all right? But here were the results that I got, all right? So in fact, I got 6 of them out of my 20 to be two heads. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I got 11 of them to have a head and a tail, and I got 3 of them to be two tails. All right, and again, that's just what I did. Right? I just sat there, flipped two, flipped two, flipped two, kept putting dots up, and then created this beautiful dot diagram. All right, now, these are my results. If you want to work exactly with me, that's fine. Write these things down. I think these are pretty representative of what most of us would see, although, quite frankly, you could have gotten really, really massively lucky, and all 20 of them could have been two heads. That, again, would have been remarkable, but hey, things happen. People win the lottery, right? Stuff like that. But that being said, let's take a look at letter C. Based on your dot plot above, state the probabilities out of 20 of each of the events that you wrote down in A. Express as both fractions and percentages. Apparently, I can't talk right now. All right, so it's easy, right? For me at least, right, the probability that I got a head and a head, right? That's 6 out of 20, all right? I can easily convert every single one of these to a percent because 20 is easily scalable to 100 by multiplying by 5 in both cases. So that's 30 out of 100, which is 30%. Granted, I'm not going to apparently have enough room for all three of these, but there we go, right? So the probability that I got a head and a head was 6/20ths, or 30%, right? What I'd like you to do now is pause the video and figure out the probability of getting a head and a tail and a tail. I would suggest doing it for your own numbers, but again, if you didn't run the experiment and you just want to do it with my numbers, that's fine too. And then we'll get those two additional probabilities in a moment. Pause the video now. All right, so let me see if I can squeeze them in here. The probability that I got a head and a tail would be 11/20ths, all right? And if I converted that into a percent by multiplying both top and bottom by 5, it would be 55%. And the probability that I got a tail and a tail would be 3/20ths, which again, if I multiply numerator and denominator by 5, would tell me 15%. All right. Now, if we had a uniform probability going on here, we would expect roughly 33%, 33%, and 33%, which would add up to 99%, and they really should add up to 100%, but you get my idea. Each one of them would roughly have the same probability, but that definitely does not seem to be what's going on here. And in fact, right, letter D, which of the three events was most likely based on your probabilities in C? Well, that was getting one head and one tail, right? For me, at least, that was the most likely. Now, you could have gotten something different, but spoiler alert, this is what we would expect. So we would expect getting one head and one tail to be the most likely of these three. So these are not equally likely outcomes. A head and a head, a tail and a tail, those should have been equally likely. For me, they weren't, all right? So I did get more of these than I got of these, all right? But this is definitely your clear winner. So let's take a look at the last question in this problem. Can you think of a reason why this event would be more likely than the other two? All right, why do I have more dots above this one than I do above these two? Pause the video now and consider that question. Now, this is really remarkable. When you put these two and these two together, you get like 9 total, and there's 11 here. So it's almost like this has as many as these two combined. It actually has more for me, right? Well, here's the reason, right? There is only one way to get a head and a head and a tail and a tail, and that's by getting heads on both coins and tails on both coins. There's only one way to do both of these two. Let me write that down. There's only one way to get both H and H and tail and tail, right? But there are 2 ways to get one of each. Now you might wonder, what do you mean there's 2 ways to get one of each? Well, it's very simple. We could get a head on coin 1 plus a tail on coin 2, or we could get a tail on coin 1 plus a head on coin 2, right? And those are 2 distinctly different things. They really are, right? They're not the same thing happening. If I get a head on the first coin and a tail on the second coin, that is a different physical thing than getting a tail on the first one and a head on the second one. So, you know, to get a head and a head, right? Well, there's only one way to do that. That's to get a head on the first coin and a head on the second coin. And likewise, tail and tail, That's a tail on the first and a tail on the second. But this one actually has twice as many ways of getting that outcome as these two. And therefore, it's twice as likely as these two to happen. Now, let's take a look at another non-uniform probability situation that's even more complicated. Here we go. Exercise number 2. For this exercise, you will need 2 standard 6-sided dice. You're going to roll both dice and record the sum of the 2 numbers showing. Letter A asks us, explain why all the sums must be from 2 to 12 inclusive. All right, meaning the smallest sum is 2, the largest sum is 12. Why does that have to be? Pause the video now and see if you can figure that out. It's pretty easy, right? The smallest sum comes from getting ones on both dice, and the largest from getting 6 on both dice. Right? So if I rolled 2 ones and added them together, I'd get a sum of 2. If I rolled 2 sixes and added them together, I'd get a sum of 12. And you can get any sum in between, right? To get a 5, you could roll a 2 and a 3. To get an 8, you could roll a 4 and a 4, right? To get an 11, you could roll a 6 and a 5. So there's, we can get every sum from 2 to 12 by either getting 2 ones or 2 sixes or anything in between. Now, if you think about that for a second, by the way, right? You can get a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 11 different sums that could come up. It almost seems like there should be 12 or 10 or something, but there's 11 different sums that could come up from 2 to 12. So let's take a look at letter B. Do you think this will be a uniform probability? In other words, will the probability of rolling any given sum just be 1/11th since there are 11 sums possible? Explain your choice. Well, I want you to just think about this a little bit. Do you think it would be a uniform probability or not? Pause the video. Well, again, I can't exactly know what your answer is. Some people might answer yes. There are 11 sums, right? So any given sum should be 1/11th. Other people might say, maybe not. Maybe they aren't equally likely. Just like in the last problem, right? We had 3 possibilities, a head and a head, a head and a tail, and a tail and a tail, but it wasn't 1/3, 1/3, 1/3. It was actually, strangely enough, 1/4, 1/2, 1/4, okay? So, this is kind of depending on just how you answered. Now, in theory, though, the answer is no, okay? Some sums are going to be more likely. But let's play around with it a little bit. All right. Now this one's going to probably take you a little bit more time, because what I'd like you to now do in letter C is I'd like you to take your 2 dice, I'd like you to roll them 30 times. Each time that you roll them, I want you to look at the 2 numbers you get, add them together, get a sum, and then plot that sum on this dot plot, okay? And this is definitely going to take you a little while because, 30 rolls, number one, you just got to keep track of how many times you've rolled. This is where it's really helpful to have a partner, who's maybe keeping track of the sums and you're rolling or whatever. But pause the video now, maybe take up to 10 minutes and produce this dot plot. All right, well again, I did my own simulation, you did yours, so your results should not be exactly the same as mine, but here's what I got, right? So if you counted up all the dots here, you'd find 30 dots, right? I got only 1 roll with a sum of 2, only 1 roll with a sum of 12. I've got, 2 rolls with sums of 9, 10, and 11. I got a lot of them with a sum of 7, quite a few with a sum of 8, quite a few with a sum of 6, all right? And then that really kind of gets into Letter D, right? Which sums were the most likely on your dot plot? Which were the least likely? Now again, this kind of depends on your particular dot plot. You may have done 30 rolls and never gotten a sum of 9, in which case, for you, that would be the least likely sum in your particular experiment. For me, the ones that were most likely, can't spell the word likely. The sums that were most likely were, they were things like 6, 7, 8. Least likely were like 2 and 12, right? So it appears like the most likely ones were these sums in the middle, and then it kind of tailed off towards the end, becoming less likely as we got away from that middle. Now, that of course leaves us right at the middle as being the most likely. And it was definitely the one that I had happen more than any of the others. So 7 came up for me more than any of the other ones, right? So our final question in Math 6, letter E. Can you think of why 7 should be the most likely sum? And it should be the most likely sum. Why is it? Pause the video now and think literally about how you come up with these sums. Well, it basically boils down to this. There are many ways to get a sum of 7. Right, so think about this. And by the way, it's even maybe more subtle than that, right? Because remember, you have 2 die, right? So let's say you had die number 1 and die number 2, right? How could you get a sum of 7? Well, if you rolled a 1 on die 1 and you rolled a 6 on die 2, that would be 7. You'd roll a 2 on die 1 and you could get a 5 on die 2, that would be a 7. A 3 on die 1 and a 4 on die 2, that would be a 7. Right? Let's try that a little bit longer and maybe extend it a little bit. We could get a 4 on die 1 and a 3 on die 2, that's a 7. A 5 and a 2, that's a 7. And a 6 and a 1, that's a 7. Right? Now, by the way, if you're looking at this and saying, oh, well, the 2 plus 5 and the 5 plus 2 are the same, no, that's not true, right? The 2 plus 5 is getting a 2 on die 1 and a 5 on die 2, right? That's it. It gives me the 7. But the 5 plus 2, that's getting a 5 on die 1 and a 2 on die 2. And if you don't like that, imagine the die have different colors. One of them's red and one of them's green, right? So you have a green 2 and a red 5 versus a green 5 and a red 2. Now, those are my sums of 7. Let's take a look at one that would be unusual. Like, let's say a sum of 11, right? How could you get a sum of 11? Well, again, you've got your die 1 and you've got your die 2. Well, a sum of 11 can actually only happen in 2 ways. You could get a 5 and a 6, or you could get a 6 and a 5, right? There are 6 different ways you can get a sum of 7. There's only 2 ways you can get a sum of 11. And at our most extreme, right, our 2 and our 12, well, for those, there's only one way to get it. A 1 and a 1, a 6 and a 6. At least for 11, we've got a 5 and a 6. The same thing kind of goes for a sum of 3, right? That could be a 1 and a 2, or a 2 and a 1. All right, a sum of 4 even gets better, right? That could be a 1, 3, a 2, 2, right? Or a 3, 1. Same thing with a 10. So as you kind of work in here, right, there's more and more ways that you can get sums of 6, 7, and 8 than there are of getting the sums out here. Therefore, giving us a very non-uniform probability with a very low probability of the sums out here and a much higher probability of getting sums in here. All right, so what's the moral of the story today? Right, all of the probability that we worked with up until this lesson all got down into these equally likely outcomes with uniform probability, meaning that every outcome that we were thinking about had the same probability of happening. Rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, rolling a 6 on a die, all equally likely. On the other hand, sometimes you can have probability problems, and I think that the coin example of flipping 2 coins is a wonderful example where, hey, there's only 3 things that can happen, and yet the probability of those 3 things isn't 1/3, 1/3, 1/3. In fact, we saw in that situation it was more like 1/4, 1/2, 1/4. Okay? So non-uniform probabilities, much more complicated than uniform probabilities, and you're going to work with them a lot more in Math 7. Therefore, we're done. We're moving on, right? This is actually, at least at this point in time, the last Math 6 video in our NGen Math 6 course. I want to thank you for joining me for NGen Math 6 and for this year of math for your 6th grade year. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.